Hey everybody. Today we're talking about functions of random variables. We're in a situation where we know the distribution of one random variable, call it x. We have a function of that random variable, call it u, and we'd like to say something about the distribution of the output, call it y. How exactly should we go about that? In order to get into this, let's consider an example. Suppose we have a random variable with a uniform distribution on the interval 0, 2, and we have a very simple function y equals x squared. We'd like to find the distribution of y. Just intuitively, y equals x squared is pushing values away from 1 in a nonlinear way, and so we shouldn't expect y to have a uniform distribution as well. We'd like to be able to find its PDF. When working with continuous random variables, we almost always want to formulate our questions in terms of the cumulative distribution function, the CDF. Let's call the CDF of y g of y, and that's equal to the probability of randomly getting a value from that distribution less than or equal to the specified value, little y. As a reminder, capital letters typically refer to random variables, lowercase letters are typically reserved for actual values that random variable might take. If we can determine a formula for g of y, for that CDF, then we'll have a full description of the random variable and we'll essentially be done. If we want the PDF, all we'll need to do is differentiate. The big idea here is to formulate the CDF of y, the thing that we're trying to find, in terms of the CDF of x, the thing that we already know. The CDF of y, by definition, is the probability that the random variable y is less than or equal to the specified value, little y. We can replace y with what it's equal to, x squared, by definition. Take the square root of both sides of that inequality, noticing that everything there is positive, so we don't need to worry about the inequality flipping or anything like that. And then at the end of that line, we have a statement in terms of the CDF of x. If we call that CDF big F, what we've got is big F of the square root of y. Since x is uniform on the interval 0, 2, its PDF is 1/2, and its CDF, the integral of that, is 1/2 x. So, plugging in big F of the square root of y, we get 1/2 square root of y for the CDF of y. Since the support of x is the numbers between 0 and 2, and y is equal to x squared, the support of y has to be between 0 and 4. So we can write out the CDF of y, g of y, more fully like this. G of y is 0 when y is less than or equal to 0. It's 1/2 square root of y between 0 and 4. And then it's 1 when y is greater than or equal to 4. Of course, this function satisfies all the requirements for a cumulative distribution function. It starts off at 0, increases towards 1. We can get the PDF by differentiating that CDF. We get 1/4 square root of y between 0 and 4, and 0 otherwise. The graph of this PDF makes it clear that the distribution of y is not uniform, just as we kind of suspected at the start of this video. The technique that we just used is very general. It's called the CDF technique or the cumulative distribution function technique. If u is any increasing function of the random variable x, then the exact steps that we used in that last example can be used to compute the CDF of u of x, as long as the CDF of x is known. So the steps from that last example are shown right here. I've written the formula for the CDF of y, replaced y with u of x, taken the inverse of u on both sides of that inequality, and then arrived at a formulation for the CDF of y in terms of the CDF of x. Notice that this does rely on the fact that the function u is strictly increasing. We can get the support of the new random variable y just by applying the function u directly to the support of x. The technique also works when the function u is decreasing, just with one small modification. The first few steps here are the same. We get the probability that u of x is less than or equal to y, but now when we apply u inverse to both sides of that inequality, we have to reverse the sense of the inequality. When you apply an increasing function to both sides of an inequality, the sense of the inequality stays the same. When you apply a decreasing function, it flips. So the probability that x is greater than or equal to u inverse of y is 1 minus the probability that x is less than u inverse of y. So 1 minus big F of u inverse of y. Things get more complicated when the function u isn't monotonic, as in this next example. Let x have the PDF 1 over theta e to the negative x plus 2 over theta for x greater than negative 2, where theta is greater than 0. Let y be the function absolute value of x. Notice that this function is not monotonic when x is greater than negative 2. We want to find the PDF and support of this new random variable y. Let's start with the support. The support of x is the set x greater than negative 2. Y is equal to the absolute value of x, so the support of y is all the real numbers greater than or equal to 0. Before we do any actual computations, let's do a little bit of intuition about the sort of thing we're going to get at the end of all of this. When y is greater than or equal to 2, we expect that random variable to have the same PDF as x, since the relationship between the variables is 1-to-1 there. In fact, it's just y equals x. That isn't the case for smaller values of y, and we can see that just by looking at the supports up above. When x is between negative 2 and 0, those values are going to map to y values between 0 and 2, as well as when x is between 0 and 2. Those values are also mapping to the y values between 0 and 2. Okay, let's compute the CDF of x. By definition, big F of x is the integral from negative infinity to x, f of t dt. In other words, of the probability density function. I've used t rather than x inside that integral to avoid reusing the letter x, which is already a limit of integration. That letter t is called a dummy variable, by the way. Carrying out that integration, we get the CDF as 1 minus e to the negative x plus 2 over theta for x greater than negative 2. For the application we have in mind, it's going to be helpful to have a bit more full description of that CDF. Rather than just saying what it is for x greater than negative 2, let's also write down explicitly that the CDF is 0 for x less than or equal to negative 2. And you'll see why that's important in just a slide or two. We're now ready to compute the CDF of y. We're going to start off just using the same steps as we did before with the CDF technique. The probability that y is less than or equal to any specific value little y. It's the probability that the absolute value of x is less than or equal to little y, which is the same as the probability that negative y is less than or equal to x is less than or equal to positive y. That's what it means for the absolute value of x to be less than or equal to the value y. So that probability statement can be written just in terms of the CDF. It's big F of y minus big F of negative y. We have that full formulation of big F from the last slide. I wrote the abbreviated version here. So we can write explicitly a full formulation of big F of negative y. We get big F of negative y as 1 minus e to the negative 2 minus y over theta for y less than 2, and 0 for y greater than or equal to 2. Combining that with what we have for big F of y, we can get g of y. It's written here. I don't think I'll read it out loud. It's quite a mouthful. You can confirm directly that g of 0 is 0, the limit of y going to infinity of g of y is 1, and g of y is increasing. So it has all the properties of a cumulative distribution function, just like we would hope. Differentiating big G gives us the PDF of y, little g, and you can see it's written here. Here's the picture that we get if we were to sketch that. Interestingly, the greatest probability density is just below the value y equals 2.